Okay, so thanks everyone being here. So today we will talk about the DBI detection and the escape. So my name is Xiaoning Li. I'm the security researcher. So this work is joint work with my friend Dr. Ke Sang and Dr. Yao. So they all work together to build different escape capability. So before our talk, we want to review the typical DBI architecture firstly. So today, if you look at the DBI implementation, the most important part is you can provide the capability to translate the native code as JIT compiler to another native code. During this phase, you can insert the instrumentation framework or capability to target the code. That's a way you can monitor the binary today to do the binary translation, this kind of thing. So here we just list the basic component. For example, you have to implement the JIT compiler to translate the native to native. And also the target code will be kept in code cache. So that's the basic memory. You put all target code in code cache and execute, but at the same time, you can monitor the code behavior. So because you want to do the instrumentation, so you have to call back to the instrumentation framework in DBI. Then you can do some cool stuff. For example, you say, I want to count how many instructions this code used, right? You can use this kind of interface to inspect every instruction and get counter, get the behavior, this kind of thing. Also, the instrumentation framework itself has to access some OS resource. So you can have the emulation interface, this kind of thing. So this picture basically shows the whole architecture if you want to build this kind of DBI capability. So that's a way you can build that. So DBI is very interesting and very powerful tool. In past years, people did a bunch of research, say, how can we detect the DBI? The reason is people use DBI to do different security usage. For example, you could use DBI to analyze malware, or you use DBI to analyze the exploit, do the exploit detection. Right? So this kind of capability will be very powerful. But if you can detect the DBI before you activate the malicious code, then of course you can avoid lots of detection. Right? That's why people do this kind of research. So here I just list the three past research about the detection part. So that's all about detect ping, detect the dynamic real. So these slides, I listed the previous methodology to detect. So of course you can use some signature like file or some strange behavior. So if you are interested in that, you can read the paper I list here to get more idea about the detection. But today we just want to talk about some new detection methodology. So we discovered and we want to share that to community, say how we can detect the DBI utility. So here we want to see we can have two different approach to do detection. So one is simple way to do the passive detection with gating code. So the basic idea is sometimes you can write some code. The code can run correctly in native mode. But if you run that in DBI environment, then DBI just crash, right? So that's very straightforward way to stop the inspection and detect the DBI this kind of environment. But that's passive way. You cannot actively detect which environment, this kind of thing. So we also will talk about a couple of approach we did to do the active detection. And with that approach, you can know, okay, so the DBI is running. And also even you can know what kind of DBI is running, right? So for the passive detection with gating code, that's pretty straightforward here. We just list the two examples, say what kind of thing you can use. Here, the first thing is the unsupported instruction. So that will be interesting because sometimes, the JIT compiler in DBI need to do the translation from binary to binary, right? So at that time, they have to do the deassembly. They try to understand the assembly code in the original code piece and translate it to target code in the code cache. So some code itself not supported by DBI environment. For example, here, the file return. So the file return not supported by pin, right? If you deassemble the pin DLL, you can see the string there, very clear. Pin does not support file return. So if you put the file return in your code, and in native mode, you just make sure the file return to correct place. But the same code, if you run with the DBI, you can see the DBI just stop. It will not go ahead to procedure following instruction. It just stops there. So another thing is it could detect the DBI with the unsupported behavior. So that means some behavior actually not supported by DBI today. For example, we found the cross-mode code itself not supported by DBI very well. So, for example, in the wall64, you want to run the code in 32-bit mode, you have to use the wall64 environment. But in same context, you could switch the code, go the 64-bit mode. That's supported by OS. So I will discuss the detail later. With that approach, you have to do the mode switch. So this one, not supported by DBI today. For example, here I put the blue box there. So in 164-bit environment, if the 32-bit running, the CS selector, the value is 23. If you are in the 64-bit mode, then the selector is 33. So if you do this kind of switch, then DBI just show you the original, the same selector. But if you code, you write the code especially for 64-bit, but the DBI didn't support 64-bit, they just run the code as 32-bit, of course you will get crash, right? That's very straightforward. So now let's back to the active detection with cross mode. So the cross mode idea is very straightforward. So today in wall64 environment, OS will support two different CS selector. Here I list say the CS 23 and the 33. So the 23 means current code running in 32-bit mode. The 33 means the current code running in 64-bit mode. So if in 32-bit mode, the CPU will decode the instruction as 32-bit instruction. But if in 64-bit mode, the CPU will decode the following instruction as 64-bit instruction. So think about the decoder algorithm or decoder mapping, probably opcode, that's sometimes totally different, right? So same code probably work in 32-bit but crash in 64-bit. But of course, maybe they can work correctly, but the meaning different, right? So why the CPU can recognize the different instruction mode? Because the CS selector in usually from the for the code segment descriptor, you can use the basic the descriptor table to search out the descriptor itself. So we have one bit called by L bit that indicate or tell CPU when the code running, which mode should be used to decode the instruction, right? So that's a basic facility there. So once you have the basic facility, then you have to transfer the mode, right? So usually we provide a couple instructions to do this kind of thing. For example, we can do the mode transfer with far jump. We can do the far call and the far return. Also, of course, we can do arret to provide the mode transfer. So here we just list example. So the DB part, we just see how you implement the assembly code to do the far jump, this kind of thing. So once you do the far branch, the CPU will automatically switch to another selector. If that selector is 33, then they switch to 64-bit. If that selector is 23, so select to the 32-bit mode. So because of the different CPU mode, they support different decoder, right? So we could support the compatibility mode. That means some compatible instruction could work for both sides. But some instruction totally different. So that's not compatible. But here we want to show some DBI detection with the compatible instruction. That could cause some interesting behavior. So for example here, let's look at the code piece here. So the left side is 64-bit instruction, right side is 32-bit instruction, but you can see the binary or the opcode totally same. The decoder itself will decode the assembly code as same. But if you run that in runtime, the behavior is different. Why? Because see the assembly code here. See, first one is move ESP to EX. Okay. So second one, that's mostly same, but second one see call, then the function return. Then you move the ESP to EBX. Then we do the sub, right? So from logic, that's totally same. But if you look at the CPU behavior, the call instruction will put the instruction to the stack and pop, because at that time the CPU the ESP operation based on 8 bytes. That's 64-bit, right? So that means if after the execution, if in 64-bit mode, then after sub the delta is 8, but in 32-bit that should be 4. So you can see the binary is totally same, but the behavior will cause a little bit different. So based on this methodology, you can easily detect the DBI environment, because when the DBI running, the DBI will not translate the selector to the 33. The JIT compiler will force that to go 23. So after the execution, you always get the delta as 4. But if you run that in native mode, the delta will be 8, right? So this is one very simple approach. We can do the DBI detection with cross-mode code. Then we look at the how other ways to do the detection. So one simple way is code cache signature. So if you look at the implementation in PIN, so they will put some special signature in the beginning of the code cache. For example, here is feed beef, right? So that's just design. So you can easily search the signature in memory. So for example, here we put the two pictures. The first one is you just search in native mode. And high likely nothing there because you're not running in the DBI environment. But if you run PIN to instrument the target code, then you can search out a bunch of signature. Here, for example, here is the 67, so a lot, right? And also because this tied to the implementation detail, so you can easily figure out you're running on PIN or in dynamic real. Of course, this case for PIN, right? So that's very straightforward. So beyond that, another approach you can detect the DBI is think about your original code. The JIT compiler will translate the original code to go code cache. So high likely the same code, but two copies in memory, right? So you can write some weird signature in assembly code to make sure your function starts from special instruction. Then you can search in memory, see how many copy in memory for similar pattern. So that's a basic idea to detect the code cache, right? So for example, here just very simple function. So left side is the signature function. So when you call this function, the DBI will translate the code to memory. Then after that, you can search. Then you found, okay, I have multiple copy. Because the original code is read-only, high likely, right? But today the code cache still read-write executable. So once you can know what's the read-write executable, what's the read-only, right? Much easier to get the idea, see which one in code cache. So, for example, here we use the code to detect the signature. Then we can find in native mode we only have one, of course, because that's the code I designed. But in the DBI mode, in pin or under pin or dynamic real, we can figure out two, because that's the way the DBI code cache works, right? So, and of course, another interesting thing is here, I'm not sure the value here is clear. So, you can always search two value. So the first value, usually the first value, just equal to the original code offset. Because, of course, after you compile the code, the offset is fixed. Nobody changes that, right? But if the code is instrumented by DBI, then you could get totally different offset. So, for example, here, by yellow color, the offset totally different. Right? That's because during the runtime translation, the JIT compiler could put the code to go different place, because it totally manipulates the code. Once the code structure and instruction deassembly correctly, so whatever, you will get correct result. But they could put the code in arbitrary place. Depends on design. So once you get multiple copy, how you detect the code is read-write executable. That's one interesting thing, because sometimes the DBI will hook the system API to block the special, for example, virtual query, this kind of function to allow you get the real property for this memory. So you have to think about how to avoid this kind of API call to detect that. So for example, the easiest way is you can try the code, try cache this kind of, try to modify the code. If you can modify code and read the same, read the content that's same as expected, of course that's writable, right? But the original code is not writable because that's in the text section and that's read only, read executable only. So now we can see another approach for the DBI detection. So, you know, the TSL is very common techniques or facility for people to enable multi-thread programming, right? You have to keep some critical data per thread. So in Windows, they have the facility like APIs, like TLS, alloc, get value, set value, and free. So that will allow you to get space in per thread memory. You put some content there. This one only tied to current thread, right? That's a basic facility to enable that. So DBI tool also need keep something per thread. So they use that. So that's very straightforward to detect DBI. And also even you can know which one. So for example here, we write code to list all thread TLS value. You see, if I didn't assign special TLS value, I expect all value from the TLS is equals 0, right? Because that's clean one and nobody uses that. But same code, if you run under DBI, then you could get totally different result. That could be interesting. Here, the first one, we run under pin. You can see the the index 1 and the index 2 equal to some pointer. That's not 0, right? Later on, we will discuss that, but you see, they have to put some critical value under that data structure, and that's the way you can detect. So here, this one about the dynamic real. So if you run the dynamic real, then you can see the later index, for example, the 53. After that, bunch of value there. So that's per design. The DBI to the dynamic real will put bunch of data there. So based this one, you can easily detect the DBI, right? Very straightforward. Okay, now we can discuss some more interesting thing. Because think about the DBI one, the DBI translation. They will do some weird thing. For example, here. So if you use the assembly code read write the EBX, then after translation, if you look at the code cache, you will see some weird result. For example, here, the instruction changed to ESI. They move the ESI go EAX, not EBX to EAX. Why they do that? Because the DBI implementation, they need to keep some critical control data structure, this kind of thing. So they are using EBX, I mean pin. especially talk to pin. So they are using EBX. So if you want to do some operation on EBX, so you will do some manipulation during the translation to avoid trouble from you, right? This is straightforward. So actually, the original EBX value will be kept in some place because the EBX are taken over by pin. So the EBX value you are using for your programming, the value back up in some place. So actually here, so once the code cache running, we will see the value in EBX point to some place. If we see the property here, you can see that's read-write executable. Then if you look at the beginning of the base address, you see that's a feedback. So that's in code cache. That means when the function, your function gets called under DBI environment in code cache, at that time, EBX point to some critical data structure, right? So they will not allow you to change that. But they have to back up the value used by original code to some place, right? So we just did some simple research and found the original EBX value put on the EBX context, code cache context, plus 24H offset. So they keep that. So now the idea is very simple. So if you can change something, correctly change the backup EBX, then you use the assembly instruction to read EBX. You don't need to specify offset this kind of, you just read the EBX. The assembly code translated by DBI will read the value from this offset because that's a backup the EBX value, right? Now you can see the EBX value you read out is some predefined by yourself. So if you put some signature there, then that's straightforward to figure out. That's under DBI environment, in pin environment, right? So we just go through 4 different active detection methodology. You can see that's very straightforward. So DBI detection is very easy, very simple. So lots of things we can do. I just list 4 different approach, new approach. So now let's back to another topic today we want to discuss, DBI escape. So you can detect DBI, you can avoid to run the malicious code, but can you run malicious code without any inspection from DBI? That will be cool, right? You try to analyze one malware, then the malware is running, but certainly they escape. Then the facility you are using totally doesn't work, even take over by malicious code. That's very dangerous, right? So we want to show some cases, see how you do this kind of thing, how we can achieve this kind of thing. But before we do that, we want to back to one simple discussion. What's mean DBI escape, right? What kind of thing we can say, okay, we are running in DBI escape. So that's about the basic different methodology or different judgment, this kind of thing. So how you think about that? So we just list couple thing here to say, we want to see, if you do this kind of thing, that's DBI escape. So first thing is bandit instruction. If you can run the file return in pin context, of course, that's escape. Because the Jetty compiler suppose remove this kind of instruction. It will not allow you to run this kind of instruction. Because once you can run the file return, that means you can switch to 64-bit mode, that's totally out of control. So if you can do that, that's one escape case. So second thing is, we talk about the EBX usage, right? So think about if in the code cache environment, you can modify EBX, point to the EBX to something totally controlled by yourself, then you take over. Because lots of critical data there, then you just take over the DBI. Of course, following you have to implement some code to totally cover DBI function, but you take over. So the third one interesting is in DBI environment, for example, the pin. So they have to run the original code in code cache, right? But at the same time, pin has own the code, do the instrumentation. So they have dedicated stack, not the same stack as OS defined for original code. So they have dedicated stack to do this kind of thing. They have to put lots of return pointer or function pointer on stack, right? So if you can run your code under DBI stack, of course you escape, because you totally control the stack part. You can initial some ROP or something, whatever. You can take over that, right? So the next one interesting is if you can run the control instruction in DBI critical context. That means in DBI environment, they try to control the target code in code cache, right? They have lots of facility data, critical context kept in code cache or someplace. If you can modify that and take over that, so you run the controlled data structure instruction with this kind of environment context, of course you escape the DBI. That's out of control, right? So of course, if you can hijack the DBI control flow, that's another thing, right? Because the DBI you can think about that's basic like sandbox. They want to run the code in code cache and fully controlled by DBI engine to make sure everything you did they can see. If you control the you change the hijack the control flow, then lots of things they cannot see. Of course, you do the escape part. And of course, if the instrumentation client totally compromised by your code, that's also you take over that. So that's all about the basic methodology or some idea, see how you break the limitation from DBI. So we want to show another one interesting here is we are using hardware feature to monitor DBI escape. Because think about whatever the code in code cache or in original code, for hardware, that's just the execution event, right? So if you can use some event to track or branch instructions, this kind of thing, of course you can get enough data, say the target code did the DBI escape. So for example, here we are using the PMU. So we designed a special tool to monitor and collect the user space application execution trace. So with that approach, we collect lots of data. Then from the data pattern, you can easily see this code did the escape or not. So here, for example, we use the utility to collect the data. If the first one, if the code running in native mode without DBI, then we collect a bunch of events. But same code, if you use the DBI to instrument, then you get pin and dynamic real. You see, the indirect call you catched from PMI, that's totally different. Because the DBI part has to inject a bunch of instruction to implement the instrumentation function, right? They have to do that. The actual code there, you have to do that. So that's a way we can collect this kind of data. So, but back to the, that's another example here. See, we collect this kind of data. See, we can collect the from to address, for example. Every time the indirect call happens, we collect the from to address. Then we get a bunch of log. So based on the data, we found some very interesting picture. So for example, here, that's a pin. We get lots of data. So the first picture here, without the DBI, then we collect the data from two log, then we draw this kind of bar, the circle. You can see if we call some very special function, the dummy function there, anything about the dummy function call, we mark that as red color, right? In the native mode, the red point, the point within the circle, the whole code circle, right? Because, of course, that's native mode. All code connection just within same program. But if you run pin with the DBI, then you can see left side. So you can, the code move up a lot because the code really running is not your original code. It's the code in code cache. So the memory layout change a little bit, right? And also, if you do the escape, then of course you can call into original code directly. You can catch the log, see the from to address related to the dummy function in memory from original code. Then you can see the red color about that function after escape case, that's still keep in similar place as previous, but that's far away from the rest of code. So you did the escape. If you don't have the escape, then you can see same picture, right side, but you don't have the red color, the point, because you never trigger that special path from hardware perspective. So that's interesting picture we show, see whether the code itself did the escape or not. So that's a facility you can monitor the whole code logic. So we did similar thing for dynamic review. That's also a similar pattern. So that's very interesting picture. So now we talk about how to what's the criteria for escape, this kind of thing, right? So now we want to talk about how we do the escape in our case. So that's back to the previous the architecture diagram. So you have a bunch of places to the escape. For example, the first one, if compiler has a bug, that you allow transfer some special code in code cache. Of course, you take over, then you can do the escape. Or you can attack the code cache to make sure the code cache running controlled code by yourself. So you can do the escape. And also you can compromise the instrumentation interface. And of course, even the emulation interface. So a bunch of we do that. So today we just list couple approach we did. So first one is code cache. So we want to do the code cache manipulation. So you can do something like you run some code, then you use other code, check the code cache, then monitor that, modify that, then run again, then probably you take over. And also you can do, say, I get code running in code cache, but the code itself will be used to address current code cache, then modify following code. Then once you call into the following code, you take over, right? So that's another approach. Then, of course, if you can change the DBS stack, you can take over, right? They have a bunch of call instruction, put the return address in stack. You change that stack, and then the stack value then point to your code, right? You can take over easily. And also, lots of pin and pin client callbacks, this kind of thing. That's writable. Then in memory, if you can change that, you take over. And also some critical data structure, right? So finally, we will use one example with us to with the file return to enable the cross-mode code. So that shows the escape part. Because file return is kind of thing banned by DBI. You should not run that. If you can run the file return and switch the mode correctly, definitely you escape the DBI. And another interesting thing is in 64-bit mode today, if you run the 32-bit DBI, in 64-bit mode, no any hook from the DBI. So this total blend, you can do whatever you want. Before that, we want to show one result people did a couple years ago, I think, for DBI escape. They talking about the approach like run the function, modify code cache, and run. So that's very interesting approach. So we show the basic result here. So the first one about, say, we run the code. Then we use the DBI instrumentation catch the call instruction counter, right? Then we run the DBI without the escape, but we run additional code, like right side. Now you can see the value here much more than the original one. Of course, because every actual code you add, every call instruction will be catched by DBI. They will add the counter. But if you do the escape, then you can see you did a lot of extra call, but the DBI facility cannot catch that because you escape the environment. It cannot catch. So similar thing for dynamic review. We got a very similar result here. So now that's another approach we talk about the self-modifying code cache. So you can build some very simple patterns. Say, I write the code itself to search the signature created by yourself. At that time, you can pending the put bunch of knobs after the signature. But during runtime, once you address that signature, you can change the code cache directly. Then after your code, then your controlled code run. Then you can take over, right? So very straightforward. So another thing here is stack. If you can take over stack, of course you can do the escape. So Here I show some very simple code piece actually from pin. That's exactly way they manage the stack. So once the code in code cache finish, we call this kind of code to save the OS-defined stack in data structure. Then load pin itself on the stack to ESP. Then they start following function. At that time, of course, you can just, if you take over that, a bunch of data you can take, right? So here, actually, I can show another interesting data here. So if you run the instruction like E9, like here, at that time, the ESP already changed to DBI, the pin ESP, pin stack. So you see this value. So if you look at the value for this memory, you will find actually this one just within same code cache, but almost the top part. So the DBI, the pin use top part, same code cache, but top part as the stack. So if once you know that, you can easily change the value in stack, and you can change the return point, a bunch of things, right? Easily to take over. And another thing for this part is actually that's back to TLS. So previously we see TLS in under pin provides some weird value, right? But if we inspect the value, you will find some interesting thing. For example, the value here is 1930010, right? So if you look at this page at the beginning, that's also feed beef. That's pin signature, right? And if you look at the 1C offset, that's exactly value used in code cache context as EBX. That's a critical data structure there, right? So that means with TLS, you can easily address this kind of critical data structure. If you replace TLS, replace TLS, then you can easily provide fake data. Then that's the EBI running your controlled context. You can totally take over that. So another critical data here is you see the pin has some special segment. For example, the .char MVE, and also in pin plugin, they also include another one like pin client. So bunch of critical function in pin client, this kind of place. So if you change that, you just you just allow your code called by pin in pin environment. So at that time, of course, you take over the whole system, the pin DPI environment. So here is one example. So in pin callback, you see some data you can easily change, but that data could be used as callback, or some data from that one could be used as callback. So that means you can control, right? So, of course, and also the in pin itself, the pin client callback is kind of itself in memory as data structure. That's another example. If you change the memory, then you can take over the control flow, because once the call happens, it call into whatever place you point to. So here is the escape demo example we did. So you see, when escape happened, the CS changed to 33, and the frame size, stack frame size as 8. So that's straightforward. And in dynamic rule, we also did a very similar thing. So now I can show one simple demo for this piece. Okay, you can see this is the native mode. I run that, so we only found one signature, then we finish. We did nothing, right? But if we want run that with pin, oh, sorry. How can I show the demo? Oh, thank you. Yeah. So if we want to run that with under pin, so this one, yes. So the code will search the signature. Then they found the code in code cache, this kind of place. Then we can manipulate. Then we can enable file call, right? Then you can see we totally take over the DBI and translate the code go 64-bit mode. Now after that, you can run uptracing. Nothing will be monitored by DBI. So if you do the malicious code or something, they never can see that. So that's an escape. So we run the same code for dynamic review. So we can see the result here. Okay, still, after searching and now this one under DBI, and we also come into the X mode. So once you switch to 32-bit 64-bit mode, the DBI cannot control that. You fully take over the DBI. Okay, so this is the demo for escape part. So now we want to bring another thing. See, lots of people want to do this kind of thing for ROP defense. So our conclusion is today, if you use the DBI to do the ROP defense, you stop something, but you bring some new attack surface. For example, code cache. Huge memory, huge code cache size memory, in memory there, rewrite executable. People can easily put shellcode there and use the DBI escape done. You cannot stop, right? So that's why we think you can defend some old Explorer, but you can make the new Explorer very easier because you provide the rewrite executable buffer that we should bind for many years. So now let's summarize the talk we did. So we just discussed some new detection, DBI detection methodology. And also we discussed what kind of thing we can think about as the DBI escape. We also go through a couple example, different way to deeply discuss the DBI escape case. So we want to see that's very straightforward, very easy, right? Previously, I think lots of people think DBI escape is pretty hard or something. That's actually very easy. So DBI is very powerful tool to defend against the existing Explorer. But if you use that, today's implementation to do the defense, then actually you bring another big surface. That causes lots of trouble, right? So basically, that's it. I can take a couple questions if people have questions. Thank you. Yeah, please. Yeah, please. Yeah, to be honest, the first thing I want to say is they have a design problem. Because you run targeted code in same process without additional protection. So once people figure out the way, they easily bypass. That's the design methodology problem. But back to detail, lots of design, the detail implementation problems there. So in my mind, I think lots of trouble there. So whatever from architecture, design perspective or the implementation, lots of problems there. So DBI escape should be pretty straightforward and very easy. Yeah, thank you. Hopefully answer your question. Okay, do you have any questions? Okay, thank you very much for your time.